So what we're talking about today we're continuing with quantum mechanics, but what we're going to explain today is we're going to really explain why these ions formed the ions that they did. Like why chlorine was really chloride with a what charge, Jorge? Chloride always had a negative. Do you remember? The periodic table kind of tells you. Had a negative 1. Oxygen has a negative 2. How about sodium? Positive 1, right? All those. In the redox reaction, some compounds donate electrons, other ones accepted them. We'll explain why there's that number of electrons, why similar groups have similar chemical properties. There's a lot of background and insight that'll be really found out through today. And probably, yeah. Okay, atomic orbital energies. So we have quantum mechanics, and there's only one element known on Earth that we can actually get the exact energy levels for the electrons, and that one element was, Daisy, what element was that? Hydrogen. So these are really the solutions or the energies of the hydrogen atom. Hydrogen only has one electron, but these are its possible energies. It can't take on any energy it wants, right? So increasing energy, I don't know why this arrow's like that. Energy is going up like this. So these are all the different energies. And some energies, each energy has these different atomic orbitals, 1s, 2s. And like the 2p, well, each atomic orbital, let's back up. Each atomic orbital is drawn like that. Or sometimes they draw a box, right, for an atomic orbital. And it looks like the p's, every single p has how many of these atomic orbitals? Danielle, are your eyes that good? How many boxes are there for each p subshell? There's actually how many orbitals? Can you see it? There's actually, anybody help her? 3. Right? How about the d? 3 atomic orbitals. How about the d's? How many atomic orbitals are there? 5 atomic orbitals. Do you know why? Yeah, which quantum? Yeah, I'm just counting the number of boxes. Like there's three lines for every d. See it? They're hard to see. It's really hard to see. It looks like one big long fat one, right? And why are there? Which quantum number had to do with the number of atomic orbitals? M sub, not M sub s, M sub l. Okay, so with p. That means that little l equals right 1. Remember, little s meant l is 0, p l is 1, d l is 2, right? But let's just start with this. But you're right, m sub l is a number of orbitals. So if L is 1, M sub L can go from -1 to +1. Well, that's 3 atomic orbitals, right? If it's a D, then L is 2. Well, then my M sub L will go from -2 all the way to +2. And that's 5. So 5 atomic orbitals. So that's where this stuff is coming from. Okay? But in one of these individual orbitals, the number of electrons that fit in any particular orbital is, how many can I fit in there, Oscar? Just in one of these. Like this has 1 atomic orbital, or 1 box. How many electrons will fit in there? It's not 1. It's not any. It's 2. Right? And we're going to be pairing them up, spin down, right? I don't know if you've seen this before. That's what we're going to be doing, okay? So the answer is actually 2. So in each atomic orbital, you can fit 2. That means, like, to fill this one up, how many electrons would that take to fill up a 2p? 6, right? To fill up a d, how many would that take? to fill it up? 10, because each one, there's 5 of them. Each one can take 2, so that'd be 10 electrons. Okay, to fill it up. All right, 10 electrons to fill it up. 6 electrons to fill it up. Okay. And all of this is just an approximation, a guess, because hydrogen only has how many electrons? Hydrogen only has 1. But like I said, with computers and their approximations, this works really good. So that's what we're sticking with. So how do we know the order in which to fill atomic orbitals with electrons? How do we know the order? Well, where would you start? Daisy, where would you start on this diagram? Start at the top or start at the bottom? Start at the bottom, yeah, the lowest energy. Start at the bottom with the lowest energy. So that means you got to fill 1s first. If I can clean this up, what would you fill next? 2s. And then, Christian, you'd fill what? After the 2s, you'd fill the 2p. And then everybody, the 3s, 3p, 4s. But then it gets funky. 3d, then 4p. So you can memorize this, right? Jorge, we were talking about memorizing, how you love to do that. So, Jorge, you can do option 1 if you want, but it doesn't make me very happy because this seems like effort. I don't like effort, right? So this is the one I'm going to do. I'm going to do option 2. And I modified this a little bit from your notes. Did this just before class. But it's the same thing. Know which atomic orbitals are being filled in the different sections of the periodic table. Okay. So we have to start with, we need to come up with the same order. And you're given the periodic table on every quiz, every exam. It's in every chemistry room, so let's use it. We're going to fill the 1s first. But the 1s orbital can take how many electrons? 2. So you can't just stop with hydrogen. 'Cause I'm looking at the periodic table. That's hydrogen. I have to finish filling in. This has to be 1s also, because the 1s isn't full until I've put in 2 electrons. So after the 1s is the 2s. Okay. So I'm just following the order on the periodic table, right? 2s, that's lithium and beryllium, 3, 4, and then 5 through 10. Okay. We'll be filling in the 2p's. Then I'm going to come back and I'm going to start over here. Now I'm going over here filling in the 3s's. Then I'm going to fill the 3p's. I'm going to keep going. I'm going to fill in the 4s's. And that's with 20 electrons. That's calcium, right? So right here, that's calcium with 20 electrons. Well, what do you fill in next? It'll be the 3d. And then I'll fill in the 4p. And then I'll be filling in the 5s. And then I'll be filling in the 4d. 5p. Then I'll do the 6s. All right, and just keep filling this guy in. And this last one would be what? If you follow the order of things, how they're going. What would this under 6p probably be? 7p. So you see how this is going? Pretty much you're filling all the s's, far left, and then you're filling on the far right all the p's. Just start with 2p. 2p, 3p, 4p, 5p, 6p, 7p. Go on down. And the d's, just remember, oh yeah, the d's start with n equals 3. So you have 3d, 4d, 5d, 6d. And does it make sense? Okay. Now all of this is called the short form of the periodic table. And they do this everywhere because this entire column right here is supposed to fit right where that dot is. Right? And then this entire column is supposed to fit right where this dot is. So And the short form is just convenient, because just think how wide this thing would be if they jammed them in there. So what we're missing here is the 4F and the 5F. And I don't know if any homework even messes with the F's, but if it does, you're ready for it. Okay. So there's a couple, so know this. This will, unless you want to memorize it. Know the order in which atomic orbitals are filled. Periodic table tells you. And we'll do some of these pretty quick here. But we need to cover a couple rules first. Rules in writing electron configurations for atoms. There's only two. We have a Pauli exclusion principle, which pretty much states no two electrons, thank you, no two electrons can have the same set of quantum numbers. That's the complicated way of saying it. There's a lot easier way, and pretty much it would look something like we draw an orbital diagram. Now here, this one's an orbital diagram of nitrogen. Let's just do that one. Nitrogen has, Danielle, how many electrons? Nitrogen has 7. Okay, what do we call these numbers? She's right, 7. What do we call these numbers in blue on the periodic table? The atomic number. It's supposed to be the number of, not of electrons, it's supposed to be the number of protons, right? But if nitrogen is neutral, well, it has 7 protons, they're all positive. That means it has to have 7 electrons. Now, all those are negatives, that's why you have 7. So the atomic number is the number of protons. Because if you add electrons, remove electrons, you still have nitrogen. It's just an ion now. Okay, so nitrogen has 7 electrons. And they want an orbital diagram, so I have to draw arrows. But I'm going to be somewhere, nitrogen is somewhere around here. So that means I got to do 1s, and then 2s, and stop somewhere in the 2p. So I have a 1s, I have a 2s, and I have 2p. And remember, draw 3 boxes for the p's. So I need to fill in all 7 electrons. So I've put in the... So how you put in these electrons, these arrows, so an arrow equals an electron, right? Or you can point it down, that equals an electron. In these orbital diagrams, how many electrons fit in one orbital again, Daisy? 2. Okay, so I put in 1, point them up. The other one, the next one, to fill it, has to go in what direction? Has to go down. That is the Pauli exclusion principle, right? Because if I put them both up, they would have the exact same set of quantum numbers. Because here the m sub s, they have the same n, has the same l, they both have the same m sub s, have the same m sub l. So the only thing you can change is m sub s, so you make them point down. So I've got 5 more electrons to go. I've just used up 2. So follow Pauli's exclusion principle. 2, 4. Now I've got 3 more to go. How can I put them in the p's? Suggestion, Oscar?
Up and down.
Up and down. And then an up. Okay. It works. It's possible. It's not the ground state. That's why they said this, so that there will only be one possible answer. Because look at all the different possible answers. I could do a lot of different things here. I could go up, down, up. It doesn't matter, just 3 of them, right? So there's a lot of possibilities. So when you have these atomic orbitals that are all the same energy, that pretty much only works for the P's, the D's, and the F's, you need to fill them in a certain way to get the lowest energy. That's Hund's rule. Now, you can never have them both in the same orbital pointing in the same direction. That's Pauli. But Hund's rule gives you the lowest energy. So what I have to do is have them all pointing in the same direction, either all pointing up or all pointing down. That's Hund's rule. That's the lowest energy. Okay? So if I did this, that's possible. It's just not the lowest energy. So ground state is the lowest energy. Okay? So this obeys both Hund's rule and the Pauli exclusion principle. The homework doesn't want you to be drawing these orbital diagrams all the time. Instead, they're going to say, write the electron configuration. It's kind of a lot easier. All you do is you just do the same thing, 1s, 2s, 2p, but you don't draw the boxes. And for superscripts, you just put in the number of electrons. So it'll be 1s2, 2s2, 2p, 3. Okay? So electron configuration, superscripts. Orbital diagram, arrows. Okay, let's try this. Let's write the ground state electron configuration of arsenic. So, do they want you to be drawing arrows, Diana? Or what do they want? How do they want you to give this answer? No, they just want you to be drawing the like 1s2, and you keep going all the way until you hit arsenic. You have to fill in, I can't see that, 50-some? What is that? 33. 33 electrons. So you start with the 1s2 and keep going. Keep going what? Following the different sections that you're filling in the periodic table. So you're going to quit right when you get down, what, 2p, 3p, somewhere 4p here. Somewhere down here is arsenic. So that's where you're going to stop, 4p something. Okay? Try it. The ground state electron configuration of arsenic. So if you stop at 1s2, you just wrote the configuration for helium. So you got to keep going. Right? 1s2. 2s2, and just keep going, but stop when you hit arsenic. 33 electrons. Allison, let's pick on you. So 1s2, 2s2, then what'd you fill next? 2p, how many? 6. And you can either remember, oh, p's have 6, d's have 10, or just count them. 1, 2, 3, 4, 5, 6. 2p6. Okay. Keep going, Danielle. Now we are at neon, so we're down here. This would be 3, not P, but 3S, right? You're right here. 3S, right? 3S2. This is 1S2, 2S2, 3S2, 4S2, 5S2, 6, right? Okay, so that's 3S2. Okay, Oscar, we're at 3S2. Now we're filling this. 3P6. If we quit now, we'd be at argon, so we got to keep going. Jorge.
4S2.
4S1, 4S2. We're at calcium now. Got to keep going. Daisy. Yeah, now we're at scandium. Now we're filling in the 3D. So 3D, how many? 10. You can count them up, or just remember D's have 10. So we're at zinc. So Christian, we're not now we can finish it. 4p3. 4p1 is gallium. 4p2 germanium. 4p3 is the arsenic. Okay, a lot of writing. But there's an easier way. The noble gas core notation. It's a shorthand way to write the electron configuration of atoms. No, we have to start at arsenic with 33 electrons. 4p6 in the last one would have been krypton. No, go over here at the periodic table.
But are we going by the electrons at the top?
We said arsenic. So find arsenic on the periodic table. Right, it's right here. So this is 2p, 3p, 4p, 4p1, 4p2, 4p3. Stop at arsenic. Okay. So for the noble gas core notation, the shorthand method, what they're saying is, okay, we'll write arsenics, electron configuration, but start at the nearest noble gas core. So, Diana, where did arsenic go? Here it is. Here's arsenic. Who is the nearest noble gas to arsenic? Who would you say? Who's the nearest noble gas? Remember, the noble gases are over here. Yeah. Right? Everybody agree? Krypton looks like the nearest noble gas. But krypton has how many electrons? 36. It's not possible. Arsenic only has 33. So the nearest possible noble gas isn't krypton. It's going to be, go all the way back, argon. Okay. So the nearest noble gas is argon. Krypton's not possible, too many electrons. So argon. So now we do the exact same thing we did, but you start at argon. All right, so now we're filling in. (4s2), 3d10, 4p3. 3d10, 4p3. Okay? So it's quicker. Okay? And the noble gas core notation is what we just did. That really helps us write the valence electron configuration. The valence electrons are a big deal because why? What's so special about these electrons? Every atom has valence electrons, but there are not very many of them. They are the what? The outermost electrons. Good. They're the accessible ones. They're the ones that are going to do everything. The chemical properties, they're going to be the ones that are, if they're going to be donated, they're the ones that are lost. If you're going to be accepting them, they're the ones that are interacting with the new electrons. The other electrons are all too inner. It takes too much energy to interact with them. So these outer electrons, right, wherever they are, the outermost, those are the valence. Those determine pretty much everything in the natural world for that element. So let's write their electron configuration then. It's called the valence electron configuration. The valence electron configuration of an atom consists of the electron configuration outside of the noble gas core, or the pseudo noble gas core notation. So pretty much write the noble gas core notation, cross out the noble gas, and we should have it. Let's take a look at arsenic. So write the valence electron configuration for arsenic. So if you write the whole thing we just did, we had argon, 4s2, 3d10, 4p3. So outside of the noble gas core, that means don't want to include him, right? So if you want to write the valence configuration. Now, there's a trick that helps me. The periodic table tells me how many valence electrons there are. It's always the what number? Anyone know this? Right? The columns were called not periods but groups. The group number is the number of valence electrons. Group 1 has 1 electron, 1 valence electron, right? Group 2, 2 valence. How about these noble gases? They have how many valence electrons? 8. So there must be something special about having 8 valence electrons, because it must be super stable. Because we know they don't interact with anything. So having 8 valence electrons must be a really good thing. But all the halogens have how many? 7. How about this group right here, this boron, aluminum, gallium, has 3. So that's kind of the trick that I follow. Arsenic has how many valence electrons according to this? 5. So whatever answer we get, we better have 5 valence electrons, 5 electrons. Well, my answer here, I've got 2 plus 10 is 12. I've got 15. Way too many.
On that one, how did you get the 3?
For arsenic, that was up here, right? So what we have to do, we had to start with this 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now it's the D's, 3d10, 4p3. So you just have to memorize, oh, these are the D's, 3d, 4d, 5d, 6d. And if you know that, you'll be okay. So in my valence, I've got way too many. Crossed out argon. I also have to cross out the pseudo noble gas core, the D10. Full D subshells are extremely stable. So stable they call them, they're just like a noble gas. They say they're never going to interact, they're never going to react. They're too stable, having this whole big set of electrons paired up. So my answer is just 4s2, 4p3. Nice. How many valence electrons is that? 5. 3 and 2, 5. Got it. Okay. So which of the following orbital diagrams are not allowed due to the Pauli exclusion principle? So circle the letters of the orbital diagrams that are not allowed due to Pauli. So, Diana, what did you circle? She circled A and C. Now I can see A, right? Because look at these two guys. Exactly the same set of quantum numbers. And in C, good. These two guys are identical. That's a problem. Oscar, are there any others? This one looks okay. Now this one, D, these guys, it's okay. It's just not obeying whose rule? Not Pauli, but Hund. So it's okay. It's just not the ground state. But it's okay. So it's kind of a trick question in that sense, that it's obeying Pauli, so I wouldn't circle it, right? 'Cause it's okay. It's obeying Pauli. Circle the electron configurations that are possible, and I added D on there. So just circle it if it's possible. Okay, anybody? What did you circle? What's that? C? Possibly. I don't see anything wrong with C. All right. Anything else? That are possible. So it's, in a sense, it's kind of another trick question. They're not saying ground state. They're just saying possible. So you're right. This is definitely not ground state. Because this 1 should be back over there. But it's possible. Right? There's nothing wrong with it. It's just not ground state. So if they said ground state, you can't give B, but it's possible. Is D possible? All they did is they just promoted that. This is a good example of what they believe is going on, why Daisy's shirt is red. Because that red corresponds to a, well, not, you see red, so it's actually absorbing blue. So that color blue, the complementary color of it isn't red, is it green? I forget these complement. You're in art? You got it all over your face. But anyway, there's the color wheel. Remember the color wheel? I don't even remember the color wheel. But whatever's opposite of red. I think it's green now is what I'm thinking. So that means her shirt is really absorbing green. So is mine, right? So green is a particular energy. And maybe that energy is the energy difference between, right, to jump up. Is it really? Right, to jump up between like maybe this energy and that energy, those two orbitals. So if that exactly matches, he can absorb that energy and jump up there. Okay, he just absorbed green, and every single molecule in her shirt has to be doing that. So it's possible. It's just not the ground state is all. Okay. Give the electron configuration of the ground state of iodine. Okay. Do with and without noble gas core. Okay. Iodine. Where the heck is iodine? Okay, yeah, thanks. Iodine was way down there at 53. So they want you to go through the full thing, right? The ground state electron configuration of iodine. Using both with and without noble gas core notation. And they want electron configuration, so no boxes with arrows, just superscripts with the number of electrons. Just keep going until you get all the way to iodine. And remember to help yourself out, remember D's are 10, P's are 6s to fill them up, so you don't have to be counting all that stuff. S's are 2, they're filled up when you have 2. All right, what was the last orbital that you filled for iodine? 5p5, 2p, 3p, 4. Yeah. Go all the way. I agree with that. Until you hit 5p5. Then do the same thing with the noble gas core notation. A lot faster though. So we're just, yeah, good. For iodine, you better start at krypton. And then you're going to jump down to, yes, then you're going to jump down to 5s2. Good. Yeah, let's write out that one. We'll have krypton, 5s2, and then what? 4d10, 5p5. Good. Okay. What would you expect for the valence shell configuration? Oh, hey, let's just do the valence shell configuration of iodine. It's right here. What's the valence shell configuration of iodine? Take out the 4d10 and take out the krypton. So you'd have, the answer would be 5s2, 5p5. So you'd have 7 electrons, like Oscar said. 5s2, 5p5. So how about zirconium? Where's zirconium? Zirconium is number 40. What would you expect for the valence shell configuration of zirconium? The outermost electrons of zirconium. Write out its electron configuration. It's number 40. Zirconium is number 40. Good question. All right. So the definition of valence electrons is everything outside of the noble gas core notation, right? So zirconium's noble gas core is krypton. If we wrote out the whole thing, you'd have krypton, and then you'd have 5s2, 4d2. Now if you look at the periodic table, what's the group number for zirconium? 4. So there's a hint. Are you going to keep the D's? Yeah. 5s2, 4d2. See the group number over the zirconium? 4. So you really want 4 electrons. So 5s2, 4d2. Or just realize you always cross out D10s and noble gases. Same thing. Okay. Manganese. Last one. Manganese. Because EX6 we've kind of done already. So let's do this one. EX5. What would you expect for the configuration of the outer electrons of manganese? So it's just another way of saying valence electron configuration, but manganese is 25, atomic number 25. Danielle, what would you say it would be for manganese? The outer electrons. Right. 4s2. Oh, this isn't 4D though. This is 3D. How many? Yeah. 1, 2, 3, 4. I agree with that. 4s2, 3d5. So it has 7 valence electrons. Okay.